First link on principal component analysis. Let us go to that website at setosa.io. This is the website. It's titled Principal Component Analysis, explained visually, so there's no mathematical equations involved. So it says here, Principal Component Analysis, or PCA, is a technique used to emphasize variation. This is a term that you will see often, and it's an important term when thinking about PCA. So that using this technique, we'll be able to bring out strong patterns in the dataset. Another term that you need to be familiar with concerning PCA. It's often used to make data easy to explore and also visualize, this PCA technique. So this is a 2D example. First, consider a dataset in only 2 dimensions like height and weight. So here you see the one variable plotted against the next, for example, height against weight. The dataset can be plotted as points on a plane, but if we want to tease out variation, that means if you want to extract out patterns or variation from the dataset, PCA needs to find a new coordinate system. The new coordinate system is this PC1 against PC2 value, PC2 variable, in which every point has a new XY value. So I'll get to that later when we look through the plots. The axes don't actually mean anything physical, unlike the height and weight just now. So imagine that x is height and w is weight, so that means something physical like height and weight. But for the PC, it doesn't mean anything because they are just an extra coordinate system to take out variation from the original XY dataset. The PCs are combinations of height and weight called principal components, and that's why they are called PCs, that are chosen to give one axis lots of variation. That means it's designed, this coordinate system is designed in a way that is able to bring out the most variation for one of the component, like for example PC1 here, there's a lot of variation here, but less variation for the second component, PC2. So we can experiment with this plot. That's why I like this website, because you'll be able to see how the changes in the physical the values of the physical parameters change the variables in the not physical parameters PCs. For example, here you see x and y is correlated, strongly correlated, and the combination of x and y shows that the PC1 has a lot of variation for the PC1. But let's see if I were to move this point, just this one point for the x, and you see that the variation for PC changes. There's still a lot of variation for PC1, but there's also the variation for PC2 that's added. And if I put it closer to the line, then it becomes just a variation for the PC1. If I do it separately like this, the other way around, again, it doesn't change to PC2, it's still PC1, because in the end they look at the correlation between x and y and not x being any PC1 or PC2 values, or any particular regression or correlation being either PC1 or PC2. Now, if this is random, without any pattern, for example like that, then you see that there will be equal variation between PC1 and PC2, or almost equal variation, where a lot more variation would be for PC1 because of the distance here and less variation in PC2. It's useful for eliminating dimensions. Below, we've plotted the data along a pair of lines. So let me just reset this to the original orientation. Okay. Below, we've plotted the data along a pair of lines, one composed of the x values and the other the y values. So here you see the variation just for x, one-dimensional, from 0 to 10. And y also from 0 to 10, and you see that the variation of x and y are about the same. When I say variation, means the distance between this point and this point are the same as the distance between this point and this point. Now for PCA, it wants to collect all of the variation into one PCs and remove the variation from the other PCs. So if you compare this x and y with PC1 and PC2, you see that the PC1 has a lot more variation compared to the PC2. If we're going to only see the data along one dimension, though it might be better to make that dimension the principal component with the most variation, like this. We don't lose much by dropping PC2 since it contributes to the least variation in dataset. So most of the variation seen in this data, this line here, can be represented just by PC1, while PC2 can actually be removed or not that important because the variation is small. That is for a 2D example. This is for a 3D example, and we don't run PCs usually on 2D examples or 2D datasets. We run it for multi-dimensional or higher dimension datasets, more than 3D even. But we can only visualize up to the 3D level, so this is the best that we can see visually with the added complexity of higher dimensions than the 2D. Anything more than 3D, it's difficult to visualize. Now for this example, we see with 3 dimensions, PCA is more useful because it's hard to see through a cloud of data. So this is the XY axis of this 3D dataset, so 3 dimensions. In the example below, the original data are plotted in 3D, but you can project the data into 2D through a transformation no different than finding a camera angle. So to see the official, okay, so this is the actual data, while this is the principal components of the data. And if there are 3 axes or 3 dimensions, there will be 3 principal components. And the goal is not, we will calculate the equal numbers of principal component as there are dimensions. Like for example, 3 dimensions will give you 3 principal components. But if we, for the principal components, we're able to remove some of the dimensions, some of the principal components, and just leave with 1 or 2 or just 3 principal components from that 4 or 5 principal components that could be calculated from higher dimensions, 5 columns of data. So here we see we can rotate this, and we see how they change. So you see the variation of X, Y, and Z here. So the variations are about equal amounts, but when we run PCA, then we see that PC1 has the highest variation, PC2 has the second highest, and the third PC has the lowest variation. And to say that these 2 PCs are can be used to recreate the X, Y, and Z values more than the PC3, and PC3 can be discarded. So to see the official PCA transformation, that means the best configuration that gives the highest variation for the first PC, then we can just click on this and show that, okay, if we were to see it in this orientation, the PC1 would have the highest variation, like so, but PC2 has second and third. So second lowest variation, same as PC3. That means that the variation is captured by PC1 more than PC2 or PC3, and PC1, PC2 could be discarded. So that is a 3D example. How about a 17D example, or in other words, 17 dimensions or 17 columns? For example, here is a data set that shows the eating patterns for 4 different areas. So England, North Ireland, Scotland, and Wales. So this shows the alcoholic drinks that they consume, beverages, carcase meat, cereals, and so on. So here it's more difficult for us to see any particular pattern in the data, unlike the 2D example where you can see X and Y is correlated. So this table shows some interesting variation across different food types, but overall differences aren't so notable. Right? We see the differences, but we can't really tell the difference between them. Let's see if PCA can eliminate dimensions so that we'll be able to see how the countries differ more clearly. So here's the plot of the data along the first principal component, the component with the highest variation. Already we can see something is different about Northern Ireland, although we can't really see it here, but over in PC we can actually see, if we label the points, we see that North Ireland has different characteristics than the other 3 areas. Now see the first and second principal components. We see Northern Ireland a major outlier. So when we plot PC1 against PC2, so this is just PC1, but when we plot PC1 against PC2, we see that North Ireland is far away. This point for North Ireland is far away from the other 3 points or 3 areas. Once we go back and look at the data in the table, this makes sense. The Northern Irish eat way more grams of fresh potatoes and way fewer fresh fruits, cheese, fish, and alcoholic drinks. That means they eat more potato, let's see. So for North Island, they eat more potatoes. Where are potatoes? Fresh potatoes. Yes. If you look at this, then suddenly we see that because of this column, the variation of North Island consumption is different than the other three areas, and it's extracted. It gets extracted using this PCA technique. It's a good sign that structure we've visualized reflects a big fact of real-world geography. Northern Ireland is only of the 4 countries not on the island of Great Britain. So PCA becomes more useful once you have higher dimensional data where you're not able to see those patterns visually like this, even though this is in the phonable graph. But once you run PCA, it looks at all the data at the same time, it extracts the highest variation into PC1, and when we plot PC1 against PC2, we'll get to see some points that are different than the others, and you can group these points according to this distribution of data in that plot, such as this plot.